Welcome back to Physics 142. We've been talking about magnetism and magnetic forces, and in this video I want to do just a few different example practice problems about magnetic forces. So first of all, I want us to just think a little bit about this idea of cross products and practice the right-hand rule. All right, and so I want to make sort of a list here. All right, let's think about if we have, say, positive charge Q, and I'm going to think of particles moving in different directions. All right, so we'll have velocity of the particle. Let's say we have a particle that's going north. All right, so we'll have positive Q. We'll have V north. And let's have, here, we'll make some tables here, all right? We'll start with some positive Qs for all of these, and then we'll make a table of V and Bs, all right? And let's suppose that V is north and B is east, all right? We have a magnetic field pointing east, and the question is, how does the force point, all right? What direction is the force? Well, to think about this, all right, let's, maybe I'll draw just a little compass here on my table. All right, so we'll have this be north, east, south, and west. Right? Never eat soggy waffles or something like that is what they say, right? So we want to know what direction is the force. Well, if the velocity, so the force law, remember, F is QV cross B. All right, QV cross B. Now remember, for cross products, order is really important. All right, you always want to point first to the V direction, the velocity direction, and curl your fingers to the B direction. All right, never the other way around, otherwise you'll get the answer backwards. All right. So let's think about this. I want you to do it for yourself at home here, all right? So go ahead, point your first finger in the north direction, and then curl your other fingers in the east direction. How does your thumb end up pointing? Well, let's do that here. I'm gonna point in the north direction. I have to curl my fingers to point east, as it will flip my hand upside down. That leaves my thumb pointing into the whiteboard, all right? Into the whiteboard, which let's take into the whiteboard to be sort of the down direction. All right, I'll say into the whiteboard is down. All right, and out, and sometimes that gets indicated with a little X symbol, right? That's into the whiteboard. And then sometimes we'll say out of the whiteboard, you indicate with a little dot. All right, we'll say that's up. And so this force here, it's going to point down into the whiteboard here, right? Down into the board, because to point to east, my fingers have to flip over. All right, let's do a few other practices. All right, what if my velocity was north, but B was southwest? All right, now B is southwest. What direction is the force going to be? So think about that for just a second. All right, well, north, all right, is how V points, and then southwest is where my fingers point, down that direction. So my thumb is pointed up, so the force will be in the up direction in that case. All right, assuming positive Q, all right? What if we continue to have positive Q and we make the velocity in the east direction, and maybe B, what if we have B up? Ooh, how's that going to work? All right, now what direction is the force? Well, take your finger, point it in the east, maybe pause the video and make sure you can do it for yourself first, all right, before I do it. All right, now I'm going to do it, so I want to point with my one finger in the east direction. I curl these fingers up, and I guess I need to kind of move myself. All right, that's going to make my thumb point in sort of what is like down in your camera view, right, which is south in how I've indicated things. So we'll say that's going to give an answer that is south, right? All right, just a couple other ones here. All right, what if I have V pointing up and B pointing south? All right, if V is up and B is south, what kind of answer do you get for that? All right, I think the answer ends up being, can pause it. Okay, it ends up being east. All right. And then last, what if we have B point west and V point west? All right, what if we have them both point west? What's the answer going to be? Well, if one is west and the other is west, well, the angle between them is 0. So that means you actually get no force if they're in the same direction. All right. Now, I should note that if you instead had a negative charge, that flips things over, all right? So if instead I had a negative charge, this force, whatever you calculate, you then need to flip it the other way, all right? So the down would flip to an up and vice versa. So the sign of the charge does actually matter for the direction. Negative charges get acted on oppositely to positive charges. All right, let's do another example here. All right, so another example that I want to think about is, let's suppose that we have, I'll erase this here. All right, let's suppose that we have a particle, and we're going to have that particle move northward, all right, through a magnetic field that's directed eastward. Okay, so we're going to have a particle that moves north, all right? So we're going to have a particle that's got velocity in the northern direction, all right? And let's say that particle has a charge 2 coulombs, all right? So here's our particle. It has a charge Q, which is 2 coulombs, all right? And then we're going to have it move through a magnetic field. Oh, that's going to get in the way. So let's just, Q is going to be 2 coulombs. Magnetic field is directed eastward, all right? So we're going to have the magnetic field be in the eastward direction here. So there's the magnetic field in the eastward direction. And let's say that is a magnetic field, that the magnetic field is pretty strong. So we'll say it's a 1 Tesla magnetic field, and let's say it's moving pretty fast, all right? So, charged particles tend to fly pretty fast, so maybe, what about 3,000 meters per second, all right? 3,000, ooh, that's hard to read. 3,000 meters per second, all right? So that will be how fast our particle is moving. Well, my first question is, let's suppose that this particle deflects upward, all right? If this particle deflected upward, my question is, what would the sign of that particle be? All right, so first question, let's say it deflects up. What's the sign? Well, let's think about it. So we do our cross product. So to get the direction of the force, right, the direction of the force, we take V and we want to cross it with B. And when I do V cross B, what do I get? I get that that's into the page here, right, down into the whiteboard. And so that would suggest that the particle, if it was positive, should deflect down, right? So if it's deflecting up instead, that means that the particle must have a negative amount of charge. So it's a negative particle, all right? So if it's deflecting down, then it needs to be negative 2 coulombs worth of charge there, all right? Okay, so now we know the direction. Well, I told you the direction, it's up. So now we know it's a negative particle. So now we just need the magnitude of the force. Right, and so the magnitude of the force, the amount of force, well, that's going to be the amount of Q times the amount of speed, right, the amount of speed times the amount of magnetic field times the sine of the angle between them, right? And so what do we have? Well, we had 2 coulombs worth of charge, right? And we just take the magnitude here because we just took care of the direction stuff, right? And then we multiply times the speed here, all right? The speed, and the speed is going to be 3 times 10 to the 3 meters per second, all right? And then we multiply times a Tesla, 1.0 Tesla, all right? And then we look at the sine of the angle between them. What's the angle between them? Well, that looks like a 90-degree angle between east and north here. So that's sine of 90 is just 1. So then we can take and we can multiply all these together, right? 2 times 1 times 3, that's going to be 6 times 10 to the 3 newtons worth of force, all right, in the upward direction. All right, so there you go. That is an example then of how we would calculate magnetic force for this particular moving particle. All right, let's do one other example here. All right, one last example is so maybe this is example 1, right? So now let's consider a new situation, example 2 here, right? So for example 2, I want to think about a charge, and we'll have it be a pretty small amount of charge. Let's say it's just 10 nanocoulombs of charge, all right? So it's and we'll have it be positive, all right? Positive 10 nanocoulombs of charge. And we're going to have that charge move east at 40,000 meters per second, all right? So we're having it move in the eastern direction. Its velocity is east here, all right? East. And we'll have it go really fast, all right? 40,000 meters per second, okay? All right. Now, if this particle, let's say this particle, right, it presumably is going to have some mass, all right? And so let's give it a mass. The mass of the particle, 0.2 grams, all right? The question that I'd like to ask is, what's the strength and direction of the magnetic field that would keep the particle just moving without falling down? All right, so, what is the strength of the magnetic field? So how much B do you need to keep the particle from falling? All right, so good question. How are we going to work this out? Well, for this one, this is east. Right now, I don't actually know the direction of the magnetic field, right? I don't know the direction of the magnetic field, but I should think about, well, what direction are the forces going to be, right? So let's think for a second. Maybe maybe if I want to think about forces, maybe I can draw a free body diagram for this charge. All right, so here's my charge. It's positive charge Q. And what forces are acting on this charge? Well, we know that if it has some mass, it's going to have it's going to have gravity acting on it, right? Force of gravity. Okay, and that gravitational force is going to be m times g, right? It's mass times the acceleration due to gravity. And, but then to keep it up, right, we want a magnetic force to keep it up. So now here we're going to have magnetic force, right, will oppose the force of gravity, right, and that's what we're trying to calculate. So we know the magnetic force must be in the up direction, right? So I'm this is up and this is down in this picture here, all right? So, all right, so if I want my result to be up, then what direction must B be? All right, what direction do I need to have B? Well, let's think about it. If V is east and I need to end with an answer that's up towards you, right? You can't, there we go, end with an answer that's up, then B better be north, right? So, if this is my sort of side view of what's going on, right? And this is my north, east, west, and south compass there, all right? Then I'm going to need my magnetic field to be in the northern direction, all right? So B must be north from the right-hand rule, right, in order to have the force be up, all right? And then to get the magnitude of B, well, the magnitude of B, remember that the magnitude of the force is QVB sine the angle between them. So solving for B, what do we get? Solving for B, we get that B must be force divided by QV sine the angle between them, right? That must be B here. And so now we can plug in some values, right? So, well, first of all, how much force do we need? Well, we know that if we want no acceleration in the up-down direction, then force of magnetic field minus mg must equal 0. So the magnetic force must be mg. So we can put that in, mg over qv sine of the angle between them. And now we plug in some values, right? So what are the values? Well, m was 0.2 times 10 to the minus 3 kilograms, right? G is 9.8 meters per second squared, all right? Q, we were told Q was 10 nano, so nano is 10 to the minus 9 nanocoulombs, all right? And the velocity was huge. It was 4 times 10 to the 4, right? 4 times 10 to the 4 meters per second, all right? So we multiply all of that together, all right? And what I got as a result from multiplying all of that together, we got to make just a little bit more room on the board to write it down, all right? The result of multiplying all of that together ended up being 0.05 Tesla, all right? In the north direction, all right? So B is 0.05 Tesla north for that problem, all right? So hopefully this gives you just a little bit more sense of how we can use magnetic forces to do some calculations.